We have an example problem here. The figure shows a laser beam deflected by a 30 degree, 60 degree, 90 degree prism. What is the prism's index of refraction? Now, I'm not entirely sure why they chose to draw this laser beam so thick, but essentially we have this laser light coming in. There's no bending at this first surface because the incident angle is 0, which means the refracted angle has to be 0 as well. The light then gets to this next surface and does bend. It bends 22.6 degrees from horizontal, not from the normal line. Okay, so when we use Snell's law and talk about refraction at a surface, well, this first surface 1, we would have n of air sine of 0 degrees because that light is hitting normal to the surface. That means the angle between the light and the normal is 0. That would equal n of the prism times the sine of theta 2. But sine of 0 is 0, so theta 2 has to be 0 at this surface. I mention that because, again, this equation, Snell's law equation, can only be used at one single surface at a time. So the light comes and hits the surface over here. I'm going to draw the normal line in. I'm doing this because the theta 2 we want is this whole angle between the normal and then the direction the light is traveling in. Theta 1 is right here, the angle that that light ray makes with the normal as it comes in. N1 for this second surface is n of the prism. That's what we want. That's what the light is originally in. And 2 is n of the air, which is essentially 1. So before we can solve this, right now we have 3 unknowns. We don't actually know theta 2, theta 1, or n of the prism. So we need to look at the angles of the prism itself. So they've told us it's a 30, 60, 90 degree prism. So they've drawn the 30 at the top, the 30 degrees, the 60 degrees at the bottom right, bottom left is the one that's 90. This angle right here has to be 60 degrees. Because that laser beam could essentially just represent the base of this prism. It's horizontal, just like the base of the prism is. So if the base of the prism on the right side makes an angle of 60 degrees with horizontal, then so does the side of the prism relative to horizontal up there. Knowing that, theta 1, because we're measuring that relative to the normal, and the normal makes a 90 degree angle in here, we can say theta 1 plus 60 degrees is 90 degrees. So theta 1 must be 30 degrees. Awesome. So we now know theta 1. Theta 2 is this entire angle over here. It's going to be the 22.6 degrees plus this portion in here. But this smaller portion is 30 degrees as well, because we have the normal line and then the horizontal line. Theta 1 is the angle between those. So theta 2 is the 30 plus the 22.6 degrees. So 52.6 degrees. So again, theta 2 is the angle between the normal line, meaning the line hitting the surface at 90 degrees, So the normal line and the light ray. So all the way down to here. Well, now we have theta 2. So we can say n of our prism, I'll just use p, times sine of theta 1 we found to be 30 degrees, needs to equal n2, well the light's going out into air, so n2 is just n of air, which is 1. Sine of theta 2, we found theta 2 from the geometry of the problem to be 52.6 degrees. So plugging this in, sine of 52.6 divided by sine of 30. I'm getting 1.59. We do have 3 significant figures here. The 30, 60, 90 prism is considered to be exact. So that doesn't mean 2 sig figs, that means forever sig figs. So our limiting and deciding factor on sig figs is this 22.6 degrees. So since that is 3 sig figs, our answer should be 3 sig figs. And again, index of refraction does not have units, so it will just be 1.59.